Hello everyone. So today in this video I am going to show you how to create a quality mesh for a patient specific geometry of a blood vessel. Here we have an intracranial aneurysm with two major inlet and outlet. The outlet further bifurcates into two smaller outlets. So let's begin. The first step to create a mesh is to create different parts of the mesh so that we can impose different meshing parameters as per our requirement on different area of the mesh or the geometry, and the different parts will also help us to impose the boundary conditions before we start simulating for the fluid. So let's create the parts. For that we'll go to the part option in the tree and select create part. The first part that we want to create is the inlet, and we'll select the inlet. We'll select the inlet surface. This is the inlet patch, and once we select it we'll confirm it by the wheel button of the mouse. Once we do that, we have created the inlet. We can confirm that by unchecking the inlet. As you can see, once we uncheck the inlet, that particular surface disappears, which means that surface is now associated with the inlet part. Next, there are two outlets here, and we want to create the parts associated with those two outlets. Let's create the first outlet. We'll name it outlet 1 and select a larger outlet with the larger cross section and confirm it. Let's create outlet 2 and associate it with the other branch. So now we have the parts for the inlets and the outlets. Next we want to create parts which are associated with the wall of the blood vessel. The first wall that we want to create is the part associated with the inlet branch. We'll name it inlet wall and select the portion of the wall of the inlet branch. We'll select it and confirm it. Secondly, we'll create the outlet wall. Select the outlet wall and confirm it. Finally, we are left with the wall which is associated with the dome of the aneurysm. So we'll name that as the aneurysm wall and select it and confirm it. If you are wondering how is the surfaces separated here, how is the surface split here for the aneurysm dome and the outlet branches, you can view my other video, the link to which I will post it in the description of this video. There I have explained how to split a single surface into different surfaces for better meshing control. So here we have the surface split into the branches and the dome. Now we have almost we all almost have all the parts that we require: the inlet, the outlet, and two outlets, the inlet wall, the outlet wall, the aneurysm wall. The final thing that we need is the body of the, we need to create a material body of the mesh, so that ICM knows where to put the, where in, or on which side of the mesh ICM has to create the, on which side of the boundary does ICM wants to create the mesh. So we'll create a material body inside this mesh. To finish things off, we'll go to the create body option, and we'll select the option of centroid of 2 points, and we'll select 2 points on the screen. Let's select first point here and the other point on the other side of the aneurysm dome, and confirm. So it's suggesting to keep, we have made a mistake. We were trying to create the material point and name, and was trying to name it aneurysm wall, which is a duplicate because we already have a part name aneurysm wall. We'll name it fluid instead, and do the same process again. Create a point here and create a point on the other side, and confirm. As you confirm it, we can see that a material body is named fluid is created inside the mesh. As you can see, this the white one. So that's all. We are done with creating our parts, and now we can proceed to create the mesh parameters. For creating the mesh, let's go to the first one, which is the global mesh setup, and go for the global mesh sizing. To begin with, we'll keep the scale factor as 1, and we have to, the first thing that we have to set is the maximum element size. In order to approximate the maximum element size, let's take a measure of the inlet diameter. We'll do that by selecting the measure distance option. As you can see, the distance is almost 15 units. So to begin with, we'll keep a maximum element size which is 1/5 the size of the inlet diameter, which is 3 unit. You can begin, you can put another value also, but I would like to start with it with such a value. Second is the, will enable this curvature and proximity based refinement. Here we have the opportunity to set up the minimum value of the cell sizes. So we'll keep it to, we'll divide the maximum size of the elements as by further 5, and we'll keep 1/5 of the value of the maximum element as the minimum size element, minimum size limit, which is 0.6, and we'll keep the refinement value at 10. This refinement basically increases the cells whenever there is a whenever there are curvatures on the surface. If there is a sudden bend or sudden indolution on the surface, then it will automatically increase the mesh number of nodes, mesh nodes on that particular area. For now, we'll keep it at 10. Once these values are selected or values are decided, we'll go and click apply. Next, we have to select the mesh type. We'll keep it as it is, tetrahedral mixed mesh, and we'll begin with the Octa meshing algorithm, which is very robust, and so it is the best. It's always good to start with a Octa mesh. We'll keep other stuff untouched here and click apply. The third one is the prism meshing parameters, to add prism layers to the geometry, or the boundary layers to the geometry. Here I will also keep it as it is with height ratio 1.4, which means the subsequent prism layers will be 1.4 times the previous layer, and would like to go with 4 prism layers in our case. It is to be noted that we can also insert our own value here. Initial height is the height of the prism layer which is closest to the wall, and accordingly it will adjust the total height of the prism layers. However, in that case we would have to separately specify the prism parameters for all the different branches, because if we keep the same prism parameters for all the branches, then it may create a problem for the smaller branches, because it will occupy all the spaces of the smaller branches, or it may so happen that the prism layers collide into one another in the small branches. So to be safe, here we will not insert any initial height or the initial height. So we'll let ICMCFT select the height with its own algorithm, and we'll click apply. Here we have just we have just inserted the height ratio, which just means, and the number of layers. We have said that no matter which artery branch it is, all the branches, or the even, and for that matter even the aneurysmal dome, will have 4 prism layers, and the layers will increase with a size of 1.4 times the previous layer. Once we have done that, we'll go for the part mesh setup. In the part mesh setup, we have the provision to enforce different meshing parameters to different area of the geometry. This is where the splitting of the surface will help us, because in our case the region of the aneurysmal wall is our region of interest, and there we will like to have mesh which is much finer than the other regions, like the inlet wall or the outlet wall. So we'll override the maximum size which we had set as 3 initially with 1.5, which is half the size of the global size setup. So once you put 1.5, the maximum cell size in the aneurysm region will be half of the cell size of the other regions. Also, we'd like to have a prism layer in the aneurysm wall. We'll check it. We'll definitely want a prism layer at the inlet wall and the outlet wall, and we'll leave the other the prism option for other parts unchecked, because we do not want a prism layer at the outlet or the inlet surface. Once we have done that, we just click apply and dismiss. Now we go to the compute mesh option, and here we leave it as it is. We leave it at Octa robust Octa mesh method. We'll check the create prism layers, because we want the prism layer, and here for the select geometry case we can go ahead with all. In that case it will take help of all the geometries available, like the points and the curves and the surface. But what I have noticed is that for a better transition from the coarser mesh uh, on the outlets and the inlets to the aneurysm dome, it's good to delete these particular curves which was generated while we are trying to split the surface into two parts. We'll delete that curve, go to the geometry. First of all, we'll delete this curve, and second, we'd like to delete the other curve which was generated as a result of splitting the surface. Done. So create the surface. We have another curve here that also can be deleted. We'll let go of this curve also. Done. So the curves on the inside of the geometry are now deleted, and let's go for the meshing stuff again. And here, instead of geometry all, we'll keep it at visible, and we'll make the points disappear. So basically we are just suggesting ICM CFD to use curves, surface and bodies as the guiding uh, as the guidance for generating the mesh. We do not want it to use the points, otherwise the points generally constrains the algorithm to create a mesh node exactly at the point, at the position of the point. We do not want that. We just want ICM CFD to use the curves and the surface and the body to use the mesh. Once we have done that, we'll click compute. So once we click compute, it has started creating the mesh. Here we might have to wait for some time depending upon the configuration of our system. It is done with creating the meshes, but the prism layers are yet to be created. It's done now. Let's unselect the surface, and immediately we see a problem that this part of the mesh is not created for some reason. Let's create the surface once more and check is the inlet wall is there. It's there. we can also see a separate surface here. Let's delete that surface which is not required. And try to compute the mesh once more. Hopefully we will have a mesh at the inlet region this time. So the extra surface in between was creating the problem, and this time it has created the mesh for the inlet region also. Let's wait for it to finish computing the prism layers. And it is done. Let's unselect the surfaces, curves, and inspect the mesh. So it looks good, and you can see that the prism layers are created. We have 4 prism layers, and another thing that we can see is that the mesh in this particular region is much finer than the mesh at the inlet branches or the outlet branches, which we have it's because we have enforced that in the part mesh setup. We have enforced different meshing parameters for this particular region, which is our region of interest. And we can see that the prism layers are created in all the branches. First, let's check the quality of the mesh that is created, and also we can see whenever there are curvatures like this one, because of the refinement which we had put to a value of 10, the meshes are being refined in these particular areas, which is good. Let's check the quality of the mesh by using the edit mesh option. First of all, we will go to check mesh option and see if the mesh is okay, and also we'll check the click and fix it automatically option and click apply. It will run its own algorithm to check if the mesh is okay. It seems the mesh is okay. Next thing, we can check the quality of the mesh created. We'll click apply. As you can see, the minimum quality is 0.187, which is not very good. Ideally, it said that the minimum quality should be at least higher than 0.3 to have a decent mesh for fluid simulation. Also, you can see the histogram here corresponding to the, which shows the number of cells corresponding to its quality range. So in the range of 0.18 to 0.22, we have 16 cells, which is almost 0.11 0.11% of the total number of cells. We have to improve it. The first thing we can do is to remesh the whole thing using a different algorithm, which is the Delaney algorithm, and we'll use the existing surface mesh to begin with. Let's do that, and once we do that, we'll see immediately that there is an improvement in the quality of the mesh. Let's go to the volume meshing parameters and select the quick Delaney mesh method and click apply. Next thing, we'll go to the compute mesh option and uncheck the create prism layers because we do not want to create the prism layers once more, and we'll select it as the existing mesh. The input should be the existing mesh, and click compute. So it will redo the volume mesh one more time, starting with the surface mesh. Once we do that, let's check the quality one more time. As you can see, immediately there is improvement in the quality of the mesh, with the minimum quality being 0.336. We can do better. We can go to this option called smooth mesh globally and try to improve the quality further. In our first attempt, we will freeze the Penta 6 option. Penta 6 mesh. Penta 6 are basically the prism layer meshes. We do not want to change them. We'll just try to change the inner tetrahedrals to see if we can improve the mesh quality, and we want it to increase to, let's say, 0.4 because we already have 0.36 as the minimum quality, and we'll increase the smoothing iterations to, let's say, 20 and click apply. Once we do that, we have a slight improvement to 0.38, and here it is a good idea to save the project because further attempt at improving the quality of the mesh sometimes may degrade the quality of the mesh also. So we do not want to lose the mesh that we at least have now. So we'll click save project. At least we can revert back to this position later on if something goes wrong. Next, we'd like to unfreeze the prism layers this time and run the whole process one more time. Once we do that, we have a slight improvement, but not much. We'll go for 0.5 this time and apply it once again. This time we have an improvement in the quality to 0.41, which is good, and also we'll save the project one more time at this point. Let's try to improve it further. We'll go for 0.6 and apply one more time. The quality has now improved to 0.45. The minimum quality is 0.45, which is pretty good. And at this point, we'll save it again and go for an attempt at, we'll attempt to finally improve it again by putting the up to value of 0.7 and apply again. Let's see if it improves further. It doesn't. It has actually decreased from 0.45 to 0.39. So it was not a very good idea, but we are safe because we have already saved the mesh or project at the quality of 0.45. So we'll reload that particular project. We would not save it because we do not want this mesh. Instead, we want to open the mesh which has the minimum quality as 0.45. The 0.45. So this is the final mesh that we would like to output now. And we can before outputting the mesh, you can check the information about the mesh by clicking the mesh info. Here you can see the total elements in the mesh is 1.8 lakhs, which is not much, and but it's good to start with the coarse mesh to get an idea of the simulations. We can refine it further. So for outputting the mesh, before outputting the mesh, it's a good idea to have an idea of the dimension of the mesh, and you will know why in a minute. Let's find the diameter of the inlet. We had actually already done it few minutes back, and it gives us a value of around it's not on the surface. Let's do it once more. We'll make the surface visible, the curves visible, the points visible, and go for the measure distance one more time. So it gives around a value of 15.35. Of course this is unitless, but we should have an idea that what unit it should belong to. Definitely it should not be meter, because 15 meter would be too big for an aneurysm, especially for an intracranial aneurysm. Most probably it will be millimeters. So we'd like to scale the whole thing before taking an output. Also, I would like to mention that in this particular case, the output that I'm going to take will be compatible with, we are trying to make an output which is compatible with OpenFOAM, because we'd like to run the simulations in the OpenFOAM solvers. And so the output extension will be .msh, which is basically also the extension for the Fluent solver. So we'll go to the output mesh option here. We'll select the select solver and keep it as ANSYS Fluent and click apply. Next we'll go to the write input option. We may save it before trying to output it, and we'll click open. And here we have the scaling option. We'd like to scale it by 1000, I mean to make it smaller by 1000 in all directions. One more thing before making an output I want to mention is regarding the parts. We have all the important parts here. Maybe we do not require the aneurysm's ICM backup. It contains some of the geometries like points and all, but it's not necessary. We can delete that, and we will have all the necessary parts starting from the aneurysm wall to the outlet wall available. So we'll go back again to the output mesh and select as the ANSYS Fluent, and the output will save the project one more time, and we'll go with and here we'll scale it down by 1000. And we'd like to name it as the coarse mesh, because all the future mesh that we're going to mesh would be finer than this. So let's name it coarse, and also let's put 1.8, since it has a total element of 1.8 lakhs. Once you do that, we can click the option done, and the mesh will have output mesh with the .msh extension. We can check it. This is the mesh, which is 14 MB in size. Now it's not always sufficient to have only single mesh, because we have to run the grid independence test, and therefore it is always good idea to create 3-4 meshes with different mesh density. In ICM CFD it's very easy to create a mesh with uh, which is finer than this particular mesh by going to the mesh option, go to the global mesh setup, and here change the scale factor to 0.5. What it basically does is it reduces all the parameters that we have set till now by factor of 0.5, and we will click apply. We don't have to change anything, and we'll go for meshing one more time. We'll start with of course we'll start with the Octa Mesh. We'll leave the Prism parameters as it is. We'll go to the compute mesh option, select the Octa Mesh. We'll create the Prism layer one more time. We'll select the geometry feasible, but we would like to disable the points. We do not want the points to constrain the mesh, and compute one more time, and we'll replace the existing mesh. This time it will take a little bit more time, since the elements would be are smaller, and hence the number of elements will be much larger than the previous mesh. So let's wait for ICM CFD to complete the meshing process. We can already see here that the mesh that is created this time is much finer than the previous one, and the mesh at the aneurysm dome is even finer, which is a good thing. Let's wait for it to finish calculating the mesh. We can see a problem at this particular outlet, and I will mention it in a while why is it happening. And also we seem to have a problem at this particular end also. We have to rectify it. That has basically happened because we have deleted one of the part, and coincidentally it happens that that particular part actually included the curve on the outlet surface, and since the guiding curve is not there, the meshing is very, we can see there are artifacts of meshing in this particular region. We have to recreate that curve one more time, and then we'll have to go for meshing one more time. So I think we'll terminate the meshing operation in between, and go for a curve creation. At this point we see there is no curve. We'll go for the geometry, create curve. We'll go for this option, extract curve from surface, select the surface, and done. We have a curve now here. You can see it by disabling making the surface disappear. Similarly, we have a curve here, so it's not a problem, but the other outlet branch also it seems doesn't have a curve, so we'll create a curve there also, and done. We can see that a curve is selected there also, is created there also. So now we can go for meshing one more time. We'll disable points once again and compute. We'll replace the this time there should be no problem with the meshing process. Let's wait for the preliminary mesh to appear. It will take some time this time, because but we can immediately see the artifacts are not there this time. We have a very good mesh at the outlet of the smaller branch because we have created the curve. Let's wait for the prism layers to be created, and then we'll try improving the quality of the mesh. We can see the messages that are being displayed here in the uh, display window. It says that it's basically running the iteration to improve the quality of the mesh uh, prism layers. Now it's extruding the prism layer number 4, which is the last prism layer, so we're close to having a complete mesh. It says it's done, and we have the mesh ready. Looks good, much finer than the previous one. Here also we'd like to check the quality of the mesh by clicking here. The minimum quality is 0.21, which is better than the previous one, but we can do better by remeshing it using the Delaney algorithm. Let's do it. And we will not create the prism layer one more time, and we will select input as the existing mesh and select compute. It will start with the surface mesh and change the volume, the meshes in the internal inner volume, and hopefully this will improve the quality of the mesh. Let's check the quality of the mesh this time. It's 0.32 is the minimum quality, so it's good, but we can improve it further. We'll improve it before that. Let's check the mesh if it is okay or not. We'll click the check and fix its automatically option there and click apply. It will run some its own diagnostics and check if everything is okay. It says 45 48 unconnected, 46 are deleted, so it has done some correction of the mesh, and finally it outputs the minimum quality. Now we can go for improvement in the quality. First of all, we'll freeze the prism layers and we'll go for a quality improvement up to 0.4 and apply. As you see that it has improved to 0.4. Let's try to 0.5. It has not improved much, but it is already in the acceptable value. At this point you can even say output the mesh, but we'll try it further. But before that, we would like to save the project here, so that at least we have this particular mesh in case we in case something goes wrong in our future attempt at improving the mesh. The project is saved, and let's go to 0.6 and apply to see if there is further improvement with prism layer fixed. there is no improvement. It remains fixed at 0.41. So this time we would like to unfreeze the prism layer and run the mesh smoothing iterations one more time. So it has now improved to 0.45. We have an improved mesh. We like to save the project here and try to further improve it. We have a further improved mesh which is almost 0.48, which is a very good mesh. We like to save it, save the project, and go for our last attempt at improving it to 0. By writing it 0.7. 0.49 is what we have now. But in the process of improving the bias, you can also see that the prism layers are a bit distorted, but that should not be an issue. We can save this, save the project. We can see the prism layers in other branches are also distorted a bit because we have unfreezed the prism layers, which should not be an issue. And at this point, I think the mesh is already in a good shape. We can output the mesh now, and let's do that. And of course, before outputting the mesh, we would like to see the mesh information, and this time we can see the total elements are 3,57,000. So it has almost 3 times more number of cells compared to the previous mesh. So let's output it. We'll scale it down by 1000 as we have did earlier. And we would like to name it as, let's say, fine mesh, and also would like to put it as 3.57, since 3.57 is the total. 3.57 lakhs is the total number of elements that this mesh has. So we'll click done, and we're done with translation. So we can see that we have another mesh which is 29 MB in size, and this can be easily transported to OpenFOAM. It is easily compatible with OpenFOAM. So like that, we can create even finer mesh. We might need to create another finer mesh, let's say with 8 lakh cells or 15 lakh cells. We can do that easily by just changing the scale factor here. Here is 0.5. Next time we might go with a scale factor of 0.25, and let's say a further scale factor of 0.1, which will create a very fine mesh. So that's how we can create a quality mesh in ICM CFD. And that's all for today. Thank you.